Hello students, welcome back. Let us resume our discussion on L'Hopital's rule. L'Hopital's rule is a limit computation technique, and the statement is here. Let me expand the font. And the standard case is for 0 over 0 type limit, as we have here. In that case, we can calculate the limit of that fraction, 0 over 0 type limit, by taking the derivative. It works for infinity over infinity type limits too. After all, you have this fraction here, and then if you have 1 over u over 1 over v, or rather 1 over v over 1 over u, then you're going to get going back to 0 over 0 to infinity over infinity, because you see 1 over infinity is 0. So yes, it works for infinity over infinity type limits too, theoretically, but only theoretically. If the second limit that you got by taking a derivative is better than before, then okay, great. You can go ahead and work out. But if it is worse than before, then it's counterproductive. So theoretically it may work, but in practice, theoretically it may work, but in practice, maybe not. That's something you have to understand whenever you are doing L'Hopital's rule for infinity over infinity type limits. For 0 over 0 type limit, no problem, most of the time. For infinity over infinity type limits, things like this can happen. After taking the derivative, it's getting worse than before. You'll have to stop, abandon, and use some other method. You can always use asymptotic estimation. And that is particularly true for radicals. Here's another problem. If you try L'Hopital's rule, you'll see this method is not working out. Taking the derivative, you end up with negative 1/2 power, which is not an improvement. Actually, it made it worse. And then by chain rule, we have another thing multiplied, and it's pretty bad. Denominator became simpler, but then again, if you move this 1/2 power down there, then you get this kind of expression. Square root is still there, and you may have to take the derivatives again, and square root will be still there. No improvement. You'll have to do this through asymptotic estimation, like this. Be careful here, x is going to negative infinity, so you may have to work out sign here. But then again, in some cases, it works out okay. Now, I don't have any red flag here, no radical. So it's looking good. We have infinity over infinity. Polynomial, which will eventually disappear if you take the derivatives many times. An exponential, which will stay the same whenever you take the derivative. Indeed, this is a computation you get. Take the derivative, you get 2x plus 5. And here, by chain rule, we get 3 multiplied there because that's the derivative of the inside. But the exponential part stays the same. Taking another derivative, you get 2 over, well, another 3 is multiplied, so you get 9. But in any case, the exponential stay the same. In the end, what did you get? We get 2 over infinity, and that's 0. And that's typically the case whenever you have polynomial over exponential. I don't care how big the polynomial is. If it is 100 to 3, eventually it'll all disappear. After 101st derivative, it's going to go. As for the denominator, it's never going to go away because the exponential will stay the same all the time. So we went through some infinity over infinity type limits that can be worked out using L'Hopital's rule here and there, and the kind of examples that do not go with L'Hopital's rule. Radical, radical. That's what you're looking for. Radical, then no L'Hopital's rule. All right, now, do you have enough time? Okay, all right. L'Hopital's rule works for fractions only. Either 0 over 0 type, which is standard, or, in some cases, infinity over infinity types. But what if you have 0 times infinity type limit? Well, if you plug in infinity, that's infinity. And here, this is e to the negative infinity, so it's 0. So this is 0 times infinity type limit. In that case, you can change it into fraction. And easy way to change it is to move this exponential downstairs. Like this. Flip it down there. And then all of a sudden we have a fraction. It's an infinity over infinity type limit. So apply L'Hopital's rule once, twice. Okay, we are ready. Plug in and we get 2 over infinity. That's 0. Let's see. Why do I have no? Just mathematical verification. No big deal. See here? This multiplication can be changed into fraction. Move one of them into denominator. Exponential e to the negative x can go to denominator. Now we have e to the positive x. Okay, here's another problem. Another 0 times infinity type limit. X is going to 0, that's 0. And then log of x squared, that's actually negative infinity. You see, log of 0 is undefined, but if the inside is getting closer and closer and closer to 0 from the right hand side, then log function go down to 0. Remember this? Like this. And then to the left, we don't have anything because inside of the logarithm always have to be positive. But it's okay because we have log of x squared. So inside is always positive. Well, shall I show you log of x squared? Oh, okay, this time negative 2 to 2. Okay. Either way, going down to negative infinity. So this is 0 times infinity type limit. 0 times infinity. So what is it? 0 times something is always 0. Well, as a matter of fact, it'll pretty much turn out that way at this level. I mean, if you go over to a little bit higher level course, let's see, in Calculus 2, we'll see some non-trivial examples where 0 times infinity is something else. But at this level, most of the time, 0 times infinity will turn out to be 0. Still, our purpose is to apply L'Hopital's rule, so let's work out. So somehow we have to change it into fraction. How do I do that? Well, here's one suggestion. Moving this logarithm down to denominator. Like this. You see, pushing something to denominator, so you have to get negative power. Another way is to push this one downstairs. So the numerator stays as now log of x squared. And then I'm pushing x downstairs. Which is better? Both are correct equalities, but as a limit computation, only one of them is useful. This or that, which do you prefer? Well, let's try this. Take the derivative of the numerator, and that's 1. Good. Now take the derivative of denominator, alright. Let's apply the chain rule. Power comes out as coefficient, and nothing changes inside. And then subtract from some power, so we have negative 2 power. And then by chain rule, we have to multiply the derivative of the inside. So the derivative of this log of x squared function, 1 over x squared, and then times the derivative of the inside, that's 2x. Okay, good luck with calculating this. I mean, by this time, when you're doing these derivative computation, you would have already noticed, hey, this is getting worse than before. Now let's go ahead with this one. Let's take the derivative of the numerator, and that's going to be a bit challenging. 1 over x squared, alright? And then the derivative of the inside by chain rule. Now how about denominator? This is just power function, x to the negative first power. So negative x to the, subtracting 1 from the power, negative second power. We got the derivative done. Can we simplify it? As a matter of fact, we can simplify. This is 1 over x squared, but if I use power form, this is x to the negative second power. Ooh. X to the negative second power. So this and that, they cancel each other out. You're going to end up with just negative 2x. So plug in x equal to 0, so that's negative 2 times 0, you get 0. If you do it this way, then you won't be able to complete it. This is negative second power, so you can push it over to the numerator. And, oh, never mind, too complicated. Here, it looks intimidating here when you take the derivative of this log of x squared using the chain rule, but it can be done. And as for the denominator, it's just power function, so it's easily done. And here's the answer. Do I have a plot? No? In that case, let me show you. X times log of x squared here's a graph. So as I get closer and closer and closer from the right or from the left, y coordinate gets closer and closer and closer to 0. At x equal to 0, this expression is undefined, but limit exists. Okay, so much for lesson 5. See you next time.